Hi students, it's Mr. Sagers back with another video for Earth and Space Science. Today's topic is the Sun. By the end of this video, you should be able to model the lifespan of the Sun, as well as be able to explain how the Sun's nuclear fusion releases energy to Earth. Let's get to it. When was the last time you truly appreciated the Sun? The Sun is arguably the most dependable thing in our human experience. Without fail, it rises every morning and sets every evening. It gives us light to see and heat to keep us warm. Because it is such a regular companion in our everyday experience, however, it's often taken for granted quite easily. But at just a mere 93 million miles from our home planet, the Sun is a vital component of Earth's very experience. All life depends upon it. Without it, we wouldn't be here. It all started so very long ago. In fact, the Sun formed nearly 5 billion years ago. As like all other stars, the Sun was born out of a nebula of cold hydrogen and helium gases. This nebula is located approximately 30,000 light-years from the center of the Milky Way galaxy in one of its spiral arms named the Orion Spur. The solar system formed some 4.5 billion years ago as gravity within the Orion Spur caused interstellar gases to collapse into a protostar. As the protostar grew in mass, its gravitational force eventually became strong enough to power its nuclear engine, and the star we call the Sun was born. During or shortly after the formation of the Sun, other nearby matter began to swirl in a flattened disk around the newborn star. This matter was comprised primarily of interstellar gases, as well as the rocky and metal-rich leftovers from previous supernovae explosions. Eventually, matter in this swirling disk began to clump together into large bodies called planetesimals. As the planetesimals grew in size, so did their gravitational force, leading to the attraction of still more stray matter. Through time, these planetesimals evolved in size to become the planets of our solar system that still orbit the Sun today. During this turbulent time of planet building, strong solar winds blasted light gases out of the inner solar system, leaving behind the denser and rocky terrestrial planets of Mercury, Venus, Earth, and Mars. The planets Jupiter, Saturn, Uranus, and Neptune were relatively unaffected by these solar winds due to their stronger gravity and greater distance from the Sun. These gas giants make up the outer solar system and are comprised primarily of thick, gaseous atmospheres and frozen inner cores. At 4.5 billion years old, the Sun is approximately halfway through its lifespan, which will follow the predictable course of other low-mass stars. Now in its main sequence stage, the Sun will continue to produce radiant light energy through the fusion of hydrogen into helium for another 5 billion years. Eventually, however, this nuclear fuel will begin to run out. Once this occurs, the forces of gravity will briefly overpower the dying nuclear furnace until the Sun's core heats sufficiently to bring about the fusion of carbon. During this stage, the Sun will swell into its red giant form, becoming many times larger in size than that which we see today. In fact, the Sun will become so large that its outer layers will swallow the orbits of the planets Mercury, Venus, and perhaps even Earth. Our home star will slowly die by ejecting much of its matter into a planetary nebula, while also condensing under the forces of gravity into a white dwarf. Through trillions of years, the Sun will cool and fade into blackness as its remaining energy dissipates into the cold and dark reaches of space. Although over 98% of the Sun is composed of either hydrogen or helium gases, its structure is not uniform throughout. The structure of the Sun can be described through its 6 distinct layers that include the core, the radiative zone, the convective zone, the photosphere, the chromosphere, and the corona. The core of the Sun is thought to be approximately 15 million degrees Celsius and is where the gravitational forces are strongest. At this temperature and pressure, nuclear fusion takes place as the Sun forges hydrogen into the heavier element helium. This process of thermonuclear fusion is responsible for the staggering amounts of light energy produced by the Sun. As light energy leaves the Sun's core, it passes through the radiative zone. Temperatures in the radiative zone are still immensely hot, but not hot enough to facilitate nuclear fusion. For reasons that aren't fully known, light passing through the radiative zone can bounce around within this layer for hundreds of thousands of years before finally exiting into the convective zone. The Sun's convective zone is located just below the Sun's surface. At 3.5 million degrees Celsius, the convective zone is much cooler than the Sun's core. Matter within the convective zone is still hot enough, however, to exist in a plasma state, or a state of matter more energetic than a gas. This plasma rises and falls within the convective zone in regular cycles, with hot matter rising to the surface and cooler matter sinking back downward. The photosphere is the sun's visible surface, through which most of the light radiation escapes outward. Keep in mind that the photosphere is not a solid surface like that of Earth, but rather a layer of superheated gas. The temperature of the photosphere is just a mere 5,500 degrees Celsius. Light leaving the photosphere is what we see when we look up at the sun and travels the distance from the sun to Earth in just over 8 minutes. The chromosphere is the sun's lower atmosphere. Light from the chromosphere is usually too weak to be seen with our eyes, but it is occasionally possible to observe solar flares and sunspots within the chromosphere. The sun's upper atmosphere is called the corona, or crown. Like the chromosphere, the sun's corona is usually too dim to be seen with the naked eye, but is sometimes visible during a solar eclipse. Curiously, the sun's atmosphere actually increases in temperature with altitude, and the outer reaches of the corona can reach temperatures of 2 million degrees Celsius. Due to the sun's gravity, the Earth is locked into an elliptical orbit some 93 million miles from the sun. As it completes its 365-day journey around the star, Earth experiences uninterrupted radiation as light from the sun endlessly bombards our home planet. Infrared radiation heats the Earth's surface and makes our home planet habitable. Visible light makes it possible for us to see and is used by plants to complete the process of photosynthesis. Without photosynthesis, a most important chemical reaction, Earth's entire food web would collapse. It is interesting to note that if Earth's orbit was just a bit closer to the sun, the star's radiant energy would be too intense to make life possible. And if Earth were just a bit further away from the sun, there would be too little radiant energy to sustain life. Thus, Earth occupies a special place in the solar system that has been given the nickname the Goldilocks, or habitable zone. Not too hot, not too cold, just right. So to recap, the sun was born 4.5 billion years ago out of a nebula in the Milky Way galaxy. The sun is now in its main sequence stage and is expected to continue nuclear fusion for another 5 billion years before collapsing into a white dwarf. The 6 layers that make up the sun each have unique properties that can be studied to learn more about our nearest star. And the sun's radiant energy makes life possible on Earth because of its special location within the habitable zone in our solar system. Well, that wraps up our video on the sun. I hope you enjoyed it and look forward to seeing you next time. Until then, Ad Astra.